Yeah, you know.
Hmm. So we'll start the lecture. Today we will study what is called a filter circuit. And in our lecture on rectifier, we have talked about rectification process in which we have converted this sinusoidal alternating current signal into unidirectional current signal like this, the one shown here, like there is no reversal in or change in the direction of current in the case of this direct current that is the output of your rectifier. But as we said, when we study the full wave and the half wave rectifiers, we have seen that there is still a very large ripple factor, 1.21 in the case of half wave rectifier. And in the case of full wave rectifier, if I remember it correctly, I think it was around 4.2 something in the case of full wave rectifier. So it was around 4.2 or 4.6 that I don't remember exactly. So that means in a rectified output here, we still have significant amount of alternating current AC component. We still have significant amount of alternating component in the output of a rectifier. So a filter circuit is an electronic circuit component which filters out AC, or you can also call it ripple component. AC or ripple component in rectifier output. Which filters out AC or ripple component in rectifier output. Okay, so that is what we are going to do, filter circuit. How we are going to filter out? We can do it using what is called C filter, using a capacitor connector connection and also an inductor connection. So this is your center tap full wave rectifier. Remember, center tap full wave rectifier. So this is the output of a rectifier, where you can connect, you can measure the voltage across this output. Your output voltage across this full wave rectifier was it was like this. It was like this. It was like this. Okay, that this is between 0 to pi, pi to pi, 3 pi, and 4 pi, and it goes on like 5 pi and all. So this is the output of a rectifier where you have they still have an AC ripple component in the output, as we talk about. Right now, in order to filter out the AC component, here in what is called the C filter, we connect a capacitor here, C. We connect a capacitor C parallel with the load resistance here. So this is your load resistance, and you are connecting a capacitor C here in the output circuit. Okay, so when you connect a capacitor in parallel with this load resistance, and as you know that and this is an alternating signal, that is current as you know that this is not a constant current. So that means there is a what is that there is a what is called alternating current component. Yeah, so we can assume that the output of this rectifier contains certain AC component as well as DC component. Certain AC component as well as DC component, certain ripple component is still available in the output of a rectifier. So and I think everybody here knows that, like, if you connect a DC circuit, something like this, suppose this is plus, this is minus, and you are connecting to a capacitor C here. Capacitor, in between this there is a dielectric, so no current can pass through it. There is a dielectric and no current can pass through it across this dielectric. Therefore, if you connect a DC voltage like this, you will find that the current passing to the circuit will be zero. The current passing to the circuit will be zero. Okay. And however, if you replace your DC source with an alternating signal, of certain omega, angular frequency omega, alternating signal of certain angular frequency omega, and connect with a capacitor, you will find that alternating current can pass through this capacitor. It can pass through the capacitor in one direction in one cycle, another direction in another reverse cycle. Okay, so the impedance offered by this capacitor to such an alternating current signal is given by this. This is the impedance, and here usually you write 1 upon j omega c. So j is your complex impedance, complex number. This is minus square root of minus 1. So this is your capacitor, the impedance of your capacitor, the impedance offered by a capacitor to a flow of AC component. So just by looking at this also, omega is the angular frequency. In the case of DC signal, there the frequency is 0 because this is a flat line. In the case of pure DC, the frequency is 0, omega is 0. So therefore, in the case of DC, the impedance will be, capacitor impedance will be infinity. Capacitor impedance will be infinity. Impedance offered by a capacitor to a DC signal is infinity, because in DC signal omega is 0. Therefore, here you will find that no current can pass through this, no DC current can pass through this capacitor, right? But if you have, rather than this DC signal, if you have an AC signal here, in the AC signal, depending on the frequency omega, if omega is very large, if the frequency is very large, then the impedance offered by the capacitor will be very small. If the angular frequency of the AC signal is small, then correspondingly your impedance will be large. Right. So depending on the frequency of the AC component, the capacitor will offer certain amount of resistance or impedance. This is not exactly resistance. This is the impedance. Okay. So here, just by looking at this circuit connection also, you will find that, let me have a certain blank page. Where do I have a blank page? Anywhere? Sorry, I should have a blank page. I need a blank page. I want to write something. So let me create a blank page. Now, so your circuit is like this. This is the rectifier, and here is one diode, here is another diode, full wave rectifier with center tap, and the simple circuit was that load resistance connected directly. But now, in order to filter out the AC component, what we do is we put a capacitor here. See, so as we said, DC component can pass through this capacitor. So DC will flow directly to all the DC component. All the DC component will flow directly to the load resistance. So you will have all the DC component to the load resistance. But we know that this capacitor, depending on the frequency of the signal, it has a certain impedance 1 upon omega c, where omega is a frequency. So the AC component, if it has a very significantly large quantity of omega, the AC component will easily flow through this capacitor. Okay, the AC component will easily flow through this capacitor. So therefore, this capacitor will create some sort of bypass rod for all the AC component. So instead of the AC component passing through the load resistance like usual, it will be bypassed by this capacitor, and the AC component, most of it will not be able to reach the load current, the load resistance. It will not be able to reach the load resistance. Therefore, in this way, we can filter out the AC component by connecting capacitor in a parallel. Okay. Now, there's another concept of another way of explaining this also. Now, if you remember, the circuit is something like this. You have a capacitor and you have a load resistance RL. Now, the output of the signal or the signal you receive from here is going like this. The output of your rectifier is coming like this. It is rising up and then decreasing, rising up and then decreasing. Now, what happened is that when the voltage signal here, the output voltage is increasing like this, as it increases like this will result in between this interval, you will find that as the voltage appearing across the capacitor increases, this will result in charging of capacitor. Charging of capacitor, or charge will be accumulated. Charge will be accumulated across capacitor plates. Charge will be accumulated across capacitor plates as the voltage across this capacitor increases. Now, between this interval, that is between this to this, here the voltage appearing across the capacitor is falling down, it decreases. Now, when the voltage that is supplied to this capacitor decreases, then at that time, whatever charge was accumulated in the capacitor, it will be discharged. So between this interval, discharging of capacitor will take place. Discharging of capacitor takes place. So when like in the process of charging, this side is positive charges are accumulated, negative charges are accumulated. When the voltage across this capacitor start falling down, the voltage applied across the capacitor start falling down. So whatever positive and negative charges accumulated here will be discharged by this capacitor across the load resistance. So because of the discharge of this current, the accumulated charges here from the capacitor across the load resistance, you will find that instead of the voltage or current falling down across the load resistance, because of the discharge current, you will find something like this. This is the charging process, and during the discharge, the discharging of capacitor will prevent the current across the load resistance from dropping down to zero. The current across the load resistance from dropping down to zero, and then subsequently your output voltage, which is current into this, will also remain like this. So instead of falling down because of the discharge, it will remain like this. And then subsequently another charging process will occur, and then when it is about to fall down, the supply voltage is falling down, the charge accumulated across the capacitor will discharge again, and then it will go like this. So finally, instead of having this kind of signal here, where the voltage or current rises and drops to zero, voltage or current rises and drops to zero, we will now have something like this. Okay, so charging process will occur, and then discharging process, discharging of the capacitor will prevent the voltage across the load resistance or the current across the load resistance from dropping down to zero. So it will sort of flatten the signal. It will sort of flatten the signal like this. So that means the changing component, the ripple component is now filtered out. So the changing component, like the changing component, which is the alternating component, which rises, decreases, is now filtered out. Charging of the capacitor will take place, and then when it is about to fall down, it will discharge. So it will have a kind of waveform like this. So this is the waveform of the capacitor filter circuit, capacitor filter circuit. Yeah. Now there is another filter circuit called inductor filter circuit. We know that according to Faraday's law, induced EMF is equal to negative rate of change of magnetic flux, and the magnetic flux associated with a coil is proportional to the current passing through the coil, and the proportionality constant is inductance, self-inductance L. So your induced EMF is equal to minus of L di upon dt. Now, if you connect this induction coil in series with the load resistance here, see this is a series connection. If you connect an induction coil in series with the load resistance like this, the usual output of a rectifier was it increases and decreases to 0, it increases to its peak value, decreases to 0, increases to peak value, decreases to 0, increases to peak value, and then decreases to 0. So this is your usual output of a rectifier. So this involves as I said, ripple component or AC component, because it contains a fluctuating, that is a rising and decreasing component, right? So now if you connect inductors in series like this, here you will see that their induced EMF is negative of rate of change of magnetic flux. Negative is according to Lenz's law. So what Lenz's law tells us is that the induced EMF always opposes the cause. Okay, induced EMF always opposes the cause. Now here, if you have a rising voltage or a rising current like this, with the rising voltage here, you will have a corresponding increase in current, isn't it? So when your voltage here increases like this, the corresponding current also increases. So when you have a rising current corresponding to this increase in voltage, because of the changing current value here, because of the change in current, di upon dt, because of the change in current, there will be induced EMF. So there will be induced EMF, which is this. So the induced EMF, as you see, is opposite to the cause. It opposes the cause. That means the induced EMF will have a direction which opposes the cause. So the cause here is between this there is a rising current. So the induced EMF will result in creating a certain kind of electromotive force which opposes the cause. That means the induced EMF will try to prevent the change in current, that is the increase of current. It will try to flatten out. Okay, the induced EMF will prevent the continuous increase in the current, because the induced EMF has a direction that opposes the cause according to Lenz's law. And also between this interval from here to here, you will find that the voltage drops here in the output of a full wave rectifier. Therefore, correspondingly, the current also tends to fall down between this interval. The current also tends to fall down. So as long as there is a change in current here, again, there will be an induced EMF. So change in current is associated with induced EMF. So the induced EMF is opposing the cause. That means the falling down of current will be opposed by the induced EMF. So instead of the current completely falling down, it will try to flatten out. So the actual circuit, the actual result will be something like this. It will try to flatten out something like this. So it will be something like this. Okay. So again, from this interval to this interval, the voltage signal increases, and correspondingly the current also tend to increase. And whenever there is a change in current, the induced EMF will oppose the cause, So it will try to prevent the rising current again. So in the actual filter circuit, it will be something like this. The output of filter circuit will be something like this. So as you see, the output of a filter circuit, flattens out. The output of filters, the filter circuit flattens the signal, the output of a rectifier. It flattens the waveform of the rectifier output. It flattens the waveform of the rectifier output. Okay, so that's how this inductor filter works, because of the Lenz's law and the electromagnetic induction, which always opposes the cause. The rising current will be opposed, the falling current also will be opposed. Therefore, it will try to prevent any changes in the output voltage appearing across a load resistance. If you connect an inductor in series with the load resistance like this. Right. So that is one way of explaining this concept. And another is you can also explain it from the perspective of the impedance. The impedance offered by this capacitor, the impedance offered by an inductor is, let's say, XL. This is equal to J omega L. J is the complex number again. So if you have for a DC component, frequency will be 0. For DC component, frequency is 0 means impedance offered for DC component will be 0. So all the DC current, that is all the DC component in the output of a rectifier will pass through this filter without any obstruction, because the impedance is now 0. It will easily pass through all the DC component. Okay. Now, when you have what is called AC component, in the AC component, omega is certain, usually large, like 50 hertz or more, let's say. So when you have a certain alternating component, ripple component, there is a certain frequency, certain variation frequency. So you will have a finite value of impedance. So this impedance offered by this inductor to such an alternating ripple component will obstruct the flow of alternating ripple component, or we can say that it will filter out certain amount of that alternating current component. It will prevent it from reaching the load resistance RL. Okay, so that is one way of explaining this L filter also. You can, I hope you understand both the concept, like from Faraday's law concept as well as the impedance formula concept also. You can see that this will perform filtering of AC. So there is this thing called LC filter. In the LC filter, simply we are combining the L filter as well as a capacitor filter. L filter is connected in series, capacitor is connected in parallel. Okay, so I think you can explain the function of this L component and C component now from the reactance or the impedance concept, as well as the charging and discharging of a capacitor, and Faraday's and Lenz's law of electromagnetic induction. You can explain everything, the working. And we also have what is called pi filter. In pi filter, simply we are having L as well as two capacitors. So when you connect one inductor in series and two capacitors in parallel, then this constitutes, or this makes your pi filter. So here this capacitor here will help in filtering out certain amount of AC component, and the residual AC component which passes through this will be filtered by this L filter again. And then if there is any residual ripple component, another capacitor which is connected here again will filter out. So the output of a rectifier after this pi filter will be more or less flat DC. It will be more or less flat DC. It may not be perfectly flat line like the signal from your DC battery, but it will be as good as that flat line DC battery. All right. Now it's almost 1. I don't know how much time is still left. How much time is still left? So I have talked about this valence breakdown before. So as I said before, in a p-n junction, in the p side there is a minority. Yeah, I have. In the p side there is a minority electrons. On the n side there is a minority holes. So when you connect in what is called reverse biasing, connecting positive to n type and negative to p type, this negative power supply will give additional energy to these electrons, and these electrons will be accelerated under the action of this reverse biasing. So when it is accelerated, when the kinetic energy of this electron is sufficiently large enough, as it passes through this depletion region, it will collide with atoms in the depletion region. By inelastic collision, it transfers sufficiently large amount of energy, and that energy will result in breaking of the covalent bonding and then subsequent release of electrons. And you will have electrons like this, 2 electrons now, the original electrons as well as the newly released electron. And under the action of this external reverse biasing, these 2 electrons again accelerate, and as they accelerate, they collide again and then multiply again. So after collision, it will make more electrons, and these 4 electrons, as they accelerate, they again collide with another atoms in the depletion region, and then they may result in another 2 more electrons each, 2 more electrons each. Therefore, from a single, that is from a very few minority electrons here, from a very few minority electrons from the p side, you will be able to generate large amount of free electrons, and that kind of large quantity of free electrons or uncontrolled voltage breakdown. This is called uncontrolled voltage breakdown. Because you cannot control the amount of this avalanche process, that is inelastic collision and release of the free electrons, right? So when that occurs, ultimately a large quantity of charge carriers passing across this depletion region will result in large amount of current, and that will burn your that will generate lots of heat, and that will burn your p-n junction diode. So that will completely damage your device, and that is undesirable, as we talk about. And we say that this valence breakdown occurs at sufficiently large voltage, large reverse voltage. So large reverse voltage. If you supply large reverse voltage, avalanche breakdown, and desired voltage breakdown, that damages our device will occur under sufficiently large reverse voltage. Okay. Now, other than this valence breakdown, we also have what is called a Zener breakdown. So in a Zener breakdown is something phenomena which occurs under controlled condition usually, and this is also intentional. We can say. Now, Zener breakdown occurs usually in a special type of diode called Zener diode. Okay. In a special type of diode, Zener breakdown occurs. But in normal diode, the voltage breakdown, the undesired voltage breakdown, occurs in this phenomenon called avalanche breakdown. in a special type of diodes, we can have what is called the Zener breakdown. Now, what are Zener diodes? In order to understand the working of a Zener diode, let us just revise what we have derived. We have obtained the depletion width across a p-n junction like this. X is the depletion width across the p-n junction. Na is the density of acceptor atoms, that is the p-type doping density. P-type doping density. P-type doping density, and D is the number density of donor atoms, as we discussed before. This is N-type doping density. N-type doping density. Now, if you increase doping concentration, that is Na and Nd value, increasing doping concentration will decrease your depletion width. It will decrease your depletion width. Okay. If you decrease your depletion weight, which is X here, if you decrease the depletion weight, if you look at this expression, the electric field across the depletion region, which is potential barrier upon depletion weight. The potential barrier means potential difference across the p-n junction is called potential barrier. We have obtained this potential barrier expression also. Now, if you decrease the depletion with X value, that will result in increase of electric field across the p-n junction. So the built-in electric field, built-in electric field means without any external biasing. Okay, without any external biasing. So the built-in electric field is already quite large in the case of Zener diode. Okay, in Zener diode, the doping is done such that the doping concentration Na and Nd are quite large, and the depletion width in a Zener diode is made as small as possible. The depletion width in a Zener diode is made very small. So when we make the depletion width very small, the electric field across the Zener diode becomes very large. Okay, so here, if you have such a condition in which, let's say you have designed a Zener diode where you have a large doping concentration and the depletion width X is small. The depletion width X is small, N-type, and this is, let's say, P-type. So if the depletion width is small, there is already electric field. This side, N side is positive. If you remember the depletion region, N side is positive, P side is negative, P side is negative. So there is already a strong electric field like this. There is a strong electric field like this in the built-in electric field. Okay. Now, if you connect in a reverse biasing condition, that is P-type connect to negative terminal, N-type connect to positive terminal. So this side is positive, this side is negative in the externally connected reverse bias voltage. This is the reverse voltage, reverse bias voltage. So if you connect like this, you are supplying additional positive potential to this. You are supplying additional negative potential to this. So the addition of this VR will further result in increase of electric field. So your net electric field, resultant electric field across this p-n junction diode under reverse bias will be original barrier potential plus reverse voltage you are connecting VR upon X. So even at a small reverse voltage, it will result in very large electric field, even for small reverse voltage. Even for small reverse voltage, it will result in a very large electric field. Okay. Now, that large electric field across the p-n junction diode will be such that under such sufficiently large amount of electric field, it will have the strength to break down the covalent bonding. It will have the strength to pull out electrons from the covalent bonding. Okay, it will have the strength to pull out electrons from the covalent bonding. So let's say this is the covalent bonding at the depletion region. Now, if you have a very large amount of electric field like this, electrons from this covalent bonding will be pulled out by this electric field, and the electrons will be drifting towards this, drifting towards the n